in case anybody who's not here would like to watch it later. And so I want to show you something here that is related to our concept of water that we've been talking about. And I would like you to write a couple of things down today. And then I'm going to just do this for a minute or two, and then we'll come back and I'll give you some time to work on the assignment for today. So what I want to show you here is related to this concept of groundwater. And this is a common diagram that, do we want to see that? Yeah, all right, we'll go with this one. This is a common diagram that you see in textbooks and whatnot when this concept of aquifer is discussed. And so right now, everyone, I'd like you to write down the word aquifer. A-Q-U-I-F-E-R. A-Q-U-I-F-E-R. And this is important because this represents the way that we get our drinking water, okay? And actually, even in most cases, the water for this can of water. An aquifer is water that is stored under the ground. Now, here's the thing, everyone. The reason I wanted to bring up this picture is because this picture very commonly creates a misconception in your brain. It creates an image of what an aquifer is that is incorrect. Because when you consider this image here that's on the screen, what you see is this blue area that's under the ground, and it makes you think that an aquifer is a void that is under the ground that is filled with water. It's almost like it's an underground pool of water. It's not. Instead, that aquifer layer is actually made up of stone. And this is a common aquifer stone. Can you see it? This is called sandstone. And this particular stone is made up of little itty bitty individual grains of sand that are glued together. Here's another example of a sandstone. This one is in layers of sand that are glued together. Okay? Now, here's the part that gets interesting. If you look closely at those individual grains of sand, it turns out they would look something like these marbles. Okay? So if you consider and you look at each individual grain of sand, what you would notice is that there are spaces between each grain of sand. Little tiny spaces. The grains of sand do not fit together 100% completely and totally tight or compact. Instead, there are little spaces, okay? Those spaces can fill with air or water. So when you look at a diagram like this, one that's on the screen, and it looks blue, what you're really looking at is a layer of rock. That rock is saturated with water. So check this out. If I take my scientific beaker of science, it has water in it. I take my sandstone, in this case represented by a jar of marbles. I can pour water into this jar. And it begins to fill up. See the little layer of water in there? I can pour even more in. This is an aquifer. Now that's hard to comprehend. It's hard for your brain to understand that because what you're thinking is rock is solid. How can rock hold water like a sponge? It can hold water like a sponge because this type of rock has pores. Now, that is not the case for every type of rock. This type of rock is a metamorphic rock. This is called purple quartzite. This purple quartzite, by the way, is what makes up the rock at Devil's Lake State Park. This purple quartzite has no pores. This type of rock is not going to be a good absorber of water. You're never going to drill into this type of rock and pull water out of it. So it does depend on the type of rock. So, oh, gee, why not? For those of you that are into details and into rocks, let me share one last thing with you. This is called limestone. And when you drive around southern Wisconsin and you see roads that cut through hillsides, sometimes you'll see this tan colored rock along the hillside. And this is called limestone. This is native to Wisconsin. This is what we find under the ground here. This is not a porous rock, but it cracks very easily. It's very commonly fractured. Lots and lots of cracks and layers of rock that are made of limestone. Those cracks can fill with water, and limestone can become an aquifer because you're pulling water out of the cracks. That sounds weird. Okay. Oh, God. All right. So here's why this is important. When we think about this concept of sustainability, do you remember when we talked about this concept of sustainability? How do we live in a way that allows future generations to live like us? Water is important. If we're pulling water out of the ground to drink, to use to irrigate our crops, we have to ensure that the future generations have access to that same aquifer. So I want to introduce you to this concept of a recharge area. You see this word right here, recharge? The word recharge, that's where the well or the groundwater, the aquifer, fills back up. So whenever you see one of these water towers, like in Verona, it's this big, huge water tower, big bulb on the top. That's where our drinking water comes from. And we're taking water out of the ground, we're filling up that big, giant water tower, and then we're pushing it out to your house so you can drink it, take a shower, use it in your dishwasher, toilet, whatever, washing machine. But if all we do is take water out, then eventually that aquifer that you see in this picture is going to dry up. If that happens, you can dig a deeper hole, but eventually you won't be able to go any deeper and it will be gone. So there's this relationship between taking the water out and nature putting water back in. So when it rains and we have a surface where the water soaks into the ground, that water is recharging the aquifer, okay? So that relates to what we've been talking about. When we talk about stormwater, if it rains on our parking lot, before there was a parking lot at the high school, that water would have soaked in the ground and it would have recharged or refilled our aquifer. But now we take that water and we send it to the Sugar River and then down to the Mississippi. So one of the designs of our detention pond was to allow some of that water to soak back in the ground. And that's important because we need it, okay? All right, so now check this out, everyone. Sometimes these aquifers can be huge. A layer of rock that holds water can extend for multiple states. So what you're seeing in this picture right here is a picture of what is called the Ogallala. You can say the word if you want. It's kind of fun. Ogallala, the Ogallala Aquifer. And that aquifer extends all the way from Nebraska all the way down into Texas. And it's used to water plants that we then eat. And I want to take a moment here and just show you why this is an issue. In this diagram, Any place that is yellow, orange, or red represents an area where the water is being pulled out faster than we're putting water back in. And in some cases, this aquifer has been depleted more than 100 feet worth of aquifer. And that is going to be a problem in terms of sustainability. Okay, check it out, everyone. This is the United States of America. And when you look at our country as a whole, you should see some patterns. The eastern part is green. Those are mostly forests. There's not that many big farms in the east. There are farms, but the big farms are not found on the eastern part of our country. We have the Appalachian Mountain Range, and we have a lot of woods, a lot of forest that looks green. Now, when you get into Ohio, Illinois, Wisconsin, Iowa, Minnesota, Kansas, this part of the country, Nebraska, starts to turn a little different color green, but it's still green. That's farmland. As you move toward the Rocky Mountains, it starts to turn brown or tan. That is because it's much drier, okay? So remember that Ogallala Aquifer is right in this section right here. It's in the brown area. Why is that important? If you live in Iowa, check this out. We're going to zoom in now on Iowa. I'm going to go slow because I know Google Earth takes a little while to catch up on the iPad. So we'll take our time here. If you live in Iowa, we could do this for southern Wisconsin as well, but I like to use Iowa because Iowa is so flat. Okay, if we go to a certain zoom distance, what you start to see is a pattern. Okay, it's coming, everybody. There it is. And do you see the grid? It looks like graph paper, doesn't it? It looks like a grid. That grid is made by roads, and those roads trace a 40-acre little square. The entire state of Iowa is cut into these little 40-acre squares. Iowa's flat, so it looks literally like grid paper. Wisconsin, by the way, is also divided into 40-acre plots, but we do have a little more topography, and so it doesn't look quite as gritty. Now, let's zoom in on one of these. What does it look like? When we zoom in, what we find, and we could pick any of these, it doesn't really matter. Let's just look at, I don't know, let's look at this one. When you zoom in on one of these, what you find are lots and lots of farm fields, okay? And Iowa, of course, is farmland. And when you look at the way that these farms are planted and farmed, what you see, and we're just scrolling around here looking at farmland, what you see is that the farmers farm generally in little rectangles, okay? And those farmers, they farm from one corner of the field completely to another corner of the field. All right, so when we look at this, the whole thing is more or less green. And if you're a farmer in Iowa, what you do is you plant your field in the springtime, and then you just wait for it to rain. Okay, this is all just green. You just plant it, and then you wait for it to rain. And that's a beautiful thing about living in Iowa. Okay, you don't have to worry about whether or not it's going to rain. It's going to rain. And when it rains, your crop is going to grow. Now, they do have droughts, but for the most part, they get quite a bit of rain. Okay, so I'm going to pause here for a moment because Google Earth takes a minute to catch up. It's a lot of data to process. And I want to contrast this with what happens when we move a little further to the west. I really wanted to find one farm field, though, that looked better. Let me see if I can grab one here. This is actually Illinois, but hold on here. Let's just see if this will focus for us. Google Earth kind of pushes zoom a little bit because it's just a lot of data. So let's Come on, Google Earth. You can do it. Come on, Zoom. Do you see the little thing twirling? That means it doesn't like the amount of data we're throwing at it. But I want you to see this picture here quickly. It's worth it. All right. Come on, Google Earth. I'm just going to pause for a moment, everyone. If it doesn't load, we can move to something else, but. Okay, so when you look at this picture, this is what I want you to create a mental image of. Do you see this square right here? You see this square? If you're a farmer in Illinois, Iowa, Wisconsin, you farm from one corner to your field to the other. You plant all of it, and it all will eventually grow because it rains. So let's contrast that now with what we find as we move toward the Rocky Mountains. Okay, we're zooming out, and we're going to focus over here in a second when this loads. Holy smokes, Mr. Casey, it's slow today. Is it slow for you? Oh gosh, Mr. Casey, what is happening here? Okay, so now let's focus in on one of these tan areas. Check this out, everyone. This is a slightly different pattern. Now, as it begins to zoom in, look closely. Do you see the pattern? Do you see it? You should be able to start to see something that looks different. Can you see it? Let's zoom in a little more and we'll see if it becomes obvious. Here it comes, everyone. Holy moly, do you see the difference? It's a completely different shape, isn't it? Now what we have are all of these little circles. We've got a whole bunch of circles. Every crop is a circle. Well, what the heck is happening there? At the center of each of these circles is a hole in the ground. It looks like this. You put a tube into the ground and you access the aquifer. Then you suck the water out of the ground. Pull, really, is a better way to put it. You pull the water out of the ground and you spray it on your field. It's a circle because these fields are irrigated by a long arm. And the arm it pivots around the center of the circle. And so what you see here is an irrigation arm. The irrigation starts here in the center of the circle and it extends out this way. And then it moves. It's on wheels and it moves. As it's moving, it sprays water. The important thing to observe here, this is a good example. You can grow crops in this part of the world as long as you add water. Wherever the water ends, it's just brown. So look at this circle. You can see a distinct line where the water is not present. That is not irrigated in that spot. You don't grow any crops. Here's why this is important. Every one of these circles is a hole in the ground connected to the same source of water under the ground, the Ogallala Aquifer. And the part that is crazy is we could scroll for hundreds of miles and what we would see is the same exact pattern. Every single circle that you see is a hole in the ground connected to the same source of water. And every single day, these farmers are pulling water out of the ground. And so that's how you empty an aquifer. Okay, does that make sense? So I wanted you to see that because it relates to what we've been talking about in terms of water use. And this is one of the reasons why we want to try to absorb as much water as we can right here in Verona in our detention ponds. This is the irrigation system, by the way. It's on the bottom here. You see those wheels? And this is called spray irrigation. As it sprays, it rotates around in a circle around the farm field. Okay, so that is a little detail, and I wanted to add that because it relates to our detention pond work, and it also relates to what we're going to do next. And what we're going to do next is talk about pollution.